Okay, we were on our last talk. We just stopped before starting what T1-Rho is. T1-Rho stands for T1 weighted and the rotating frame. And just give a little historic reason what that is the laboratory
Dr. Cruz, I'm
frame.
sorry to
Can't see
Dr.
it?
Cruz, I'm sorry to interrupt. I can't see
Okay, see if that
things.
helps.
Sorry.
Okay, so so the T1-Rho stands for T1 weighted or T1 in the rotating frame. Uh, the the laboratory frame is the frame that we sit in, that the laboratory is in. The rotating frame is the frame of reference that the nuclei are sitting in. So the rotating frame spins around the z-axis at the Lamar frequency. So if you're sitting in the rotating frame, then the nuclear spins are stationary. They don't move. The whole world moves around you, but the frames don't move. In the laboratory frame, the laboratory is fixed, but the nuclei are spinning around at 64 million times a second. Uh, it turns out that if you measure T1 in the rotating frame of the nuclei, it can be slightly different or markedly different than the T1 in the laboratory frame. And the way you then measure that is what you do is before we do our regular pulse sequence, you put on a an RF pulse that forces all the nuclei to be together, and you take a weak pulse, you do the echo, and you get an echo. Then you put on a stronger pulse, you find the strength of the echo, and so forth. So you do a series of these pre-pulse, uh, uh, you do a series of experiments using different strengths of this preparatory pulse. And then you see how the signal changes going from a small to a large pulse. And that will typically be an exponential. Then you can calculate the T1-Rho from the fact that the signal intensity is equal to constants times e to the minus t over T1-Rho. And therefore you can calculate it a lot similar to the way you calculated a T2 weighted image using the cardiogram that we talked about before. It turns out when you do this that roughly what you're actually calculating here is what the T1 would be if the Lamar frequency were zero. That is, it's what the T1 would be if you're measuring it when there's no magnetic field. But we can't measure it at no magnetic field because you can't get an echo. So this is a way to trick the spins into allowing us to measure what the T1 would be if we were actually measuring it at zero magnetic field. And as we talked about before, what causes contrast with T1 is the interchange between the lattice molecules, the big molecules, and the nuclear spins. Uh, what we also talked about before, if you remember, that the efficiency of or how efficient we can actually get the Z component of bulk magnetization to grow along the Z axis has to do with how many photons from the lattice are present at the Lamar frequency. And we also said that if you remember, the large molecules tend to rotate slowly. Small molecules tend to rotate very rapidly. So T1 tends to be more efficient in small molecules at higher magnetic fields and more efficient in large molecules at lower magnetic fields. So what we're actually doing by measuring the T1-Rho is we're basically measuring the effect of large molecules on the spins. So it tends to not be very important when you're dealing with water or just very small molecules, but it may tell us something about large macromolecules like fat or proteoglycans. So T1-Rho right now is, people are experimenting it right now and evaluating articular cartilage. Primarily, there are correlations, as we talked about in the cartilage section, between T1-Rho and the amount of proteoglycan in cartilage. And in fact, maybe beginning next year, we'll try to do some of these experiments with GE, looking at different ways to do T1-Rho and see which ones are more effective at looking at proteoglycan. It's not clear that it gives too much different than T2 in the articular cartilage right now, but there's a lot of interest in it.
Like you would just see the cartilage better, or
You can measure the signal would be proportional to the proteoglycan content. So a way to measure the proteoglycan content, a lot like we talked about degemerate, except this way you wouldn't have to give contrast and you wouldn't have to wait 40 minutes for it to equilibrate. It would be a much more efficient pulse than doing degemerate if it worked out. But it's been around a long time now and it hasn't really worked out, so I'm a little suspicious. Yeah, what?
what would your standard be? Like you're saying,
The standard would be biochemical analysis, just like it was for degemerate. And the studies that Deb Bernstein did with degemerate, she correlated the signal intensity with degemerate with biochemical analysis on biopsy specimens or cadaver specimens. Okay.
And again, we're not these images are kind of more like kind of these color maps, right? That would
Yes.
show like the extent of
Right. They're usually presented in color maps because it's a little bit more obvious. It's just a little sexier when you do that. I don't think we need to go into this. And one of the other things that happen as you lower the B naught, it turns out that T1 and T2 converge, and actually at zero magnetic field, T1 and T2 become the same entity. But we don't need to go into that. This is all the stuff we just talked about. And this is just a study from the literature from 2006. And you can see here that here's a T2 map of articular cartilage, a T2 map, T1-Rho map, and then down here is actually the histologic specimen of this particular cartilage. And when you actually graph these, you find that the T2 doesn't change much depending upon the severity of the osteoarthritis, but there was a better discrimination between early OA and advanced OA on the T1-Rho measurements rather than the T2 measurements. But there have been several papers published in this area, and they don't all give the same results. So there's still a lot of question about the actual role of the two in articular cartilage right now. So if you hear about T1-Rho, that's what it is. Obviously, it's kind of a cursory description of it. Let's talk about fast spin echo, because that's what we use day in and day out now. And let's see how it's different from the standard spin echo that we talked about earlier. Okay. Let me see. No, Michael doesn't have a microphone, right? So we can't pick on Mike. Okay, let's pick on Yuri. Yuri, what's the difference between fast spin echo and standard spin echo?
It has to do with using a 180 degree rephasing pulse. So after we use a 90-degree pulse in the fast spin echo, we use 180-degree pulse to rephase the spins.
But that's what we did. That's what we did with the standard spin echo.
Okay. Oh, I'm sorry. Fast spin echo.
Okay. Well,
yeah.
Now with the standard spin echo image, what we saw is that we could do a 90-degree pulse at 180, and at TE we would get an echo. We could receive that echo putting in a frequency encoded gradient, and then we could generate our image. We also found that we could do a 90-degree pulse, 180-degree pulse, get an echo, then do another 180-degree pulse and get a second echo, a dual echo sequence, in which case we could get a short TE image and a long TE image. But they'd both be at the same location in space, so we'd have a short TE and a long TE. They would be two images, but they would be of the same body part. Okay? So those are just two separate images. Now what we'd like to be able to do is acquire imaging much faster. So can anybody come up with a way where instead of getting two images, one with a short TE and another with a long TE, we could actually acquire more data and fill up case space faster? Instead of getting more images with different contrasts, we could acquire the image for one slice much more rapidly. Rob?
I'm sure it uses gradients somehow.
Okay.
So
All right. Well, now fast spin echo is important because that's basically everything we do nowadays, either fast spin echo or fast gradient echo. So with the fast spin echo, what we get is a 90-degree pulse, 180-degree pulse. We get an echo. We do a series of 180-degree pulses with an echo after each one. Now, before we said that if we just got two or three echoes, we'd get three images, but they'd have different contrasts. But now what we do is before each of these 180-degree pulses, we put in a different phase encoding, which it's not really showing here. You put in a different phase encoded so that each one of these echoes has a different phase encoding on it. So if you do that, let's just say we have three echoes, and we put a different phase encoding on each of these three echoes. With each phase encoding, you can fill up another line of case space. So if you have three echoes that have three different gradients on them, then you can fill up three lines of case space with just one TR. And therefore, you could acquire your images three times faster than if you just have one echo per phase encoding.
So before the old technique, or the technique we went over yesterday, the standard spin echo, you do two 180s and then you do the phase encoding. There's one phase encoding.
No. The dual echo sequence that we used to do all the time, some people still do, but not very many. You do a 90-degree pulse, then you do a phase encoding, then you do a 180-degree pulse, get a signal, 180-degree pulse, and get another signal. And you'd get two images with different contrast all in the same location.
So the phase encoding, it's still one phase encoding step you went.
So both echoes have the same phase encoding, and therefore you're filling the same line of case space with each of the echoes. So you end up with two different images, but of the same body part.
Although they're coming later. You ran your phase encoding, and then you do two more echoes, and that's still, it takes those two echoes and puts it in the same phase encoding like space on case space.
That's right. So it's the same slice, so you just get two images with different contrast.
Now we're doing separate phase encoding.
Now what you're doing with each echo, you're doing a separate phase encoding, and therefore, since it's a different phase encoding, it's going to fill a different line of case space. And we try to put the echoes as close together so that they have as similar contrast as possible. So what we may have before, we would have like a 180-degree pulse at 15 milliseconds, which gave us an echo at 30 milliseconds. Then we'd have another 180-degree pulse at 45 milliseconds, which would give us another echo at 60 milliseconds. Now, if we do fast spin echo imaging, is what we're going to try to do, is do an echo, say, at 15 milliseconds, after we do a phase encoding, then do a quick phase encoding, do another 180-degree pulse at like 17 milliseconds, get another echo at 19 milliseconds, throw in another phase encoding, put in another 180-degree pulse, get another echo at like 22 milliseconds, and end up getting up to 32 or even more echoes with a single TR. And therefore, you can speed up your acquisition. Then typically what we'll do for T1 weighted images, we'll typically do somewhere around an echo train length of 3. But for most T2 weighted images, we'll do an echo train length of 8 or 16. So it used to be that T2 weighted images took forever to acquire. They were like 10 to 20-minute scans. Now with fast spin echo, if you do 16 echoes, instead of it being 16 minutes to do an acquisition, you can cut it down to 1 minute to do an acquisition. So T2 weighted images have now become very rapid image to acquire. Now, as you can see, there are going to be problems because all of your data is not coming from the same TE time. And that causes a lot of problems. it changes the contrast. And in the early days of doing this, we found that fast spin echo images were less sensitive for meniscal tears than standard sequences. So even now, I know a few people who will not do fast spin echo imaging of the knee because they're afraid they're going to miss meniscal tears. It turns out that the echoes that are important for contrast are the echoes around the center of K-space. We talked about that before. So now is what you do is you decide what kind of contrast you want. Do you want it a T1 weighted image? Do you want a proton density weighted image, or do you want it a T2 weighted image? If it's a T1 weighted image, you want to use a short TR like we talked about before, and you want the center of K-space to be your first echoes because you want a short TE. Before they would start, initially when they started, you'd start with a negative, strong negative phase encoding. You'd go up through 0, and then you'd do up to strong positive phase encodings like we talked about before. But now it's turned out that for contrast, it's better to do the 0 K-space first, then go around the 0 K-space values and not do the high levels of phase encoding until later out because they're not important for contrast. If you remember, the high values for phase encoding fill in the periphery of K-space, which is important for resolution, not for contrast. So you typically then will cluster the 0 K-space or the low phase encoded gradients around the contrast you want. So if it's T1, it's going to be short. If it's proton density, you use a longer TR, typically around 3 to 4,000 milliseconds, maybe even longer. And you can do that now because we can do this imaging so much more efficiently. But then again, you'd want to center the K-space values around a relatively short TE. A lot of people won't use the shortest. They'll use something more around 30 milliseconds for various reasons. And then if you want a T2 weighted image, you would take the high ends of K-space sooner, and you'd put the center of K-space out at later TE, say 60 to 80 milliseconds. So there are a lot of things to play with in fast spin echo imaging, and that's why it took a number of years before we came up with the modern sequences now, where we get speed and we get diagnostic accuracy at the same time. Also turns out that electronically you get a lot of crosstalk between the echoes with fast spin echo imaging. And one of the results of that is it used to be in the old days on T2 weighted images, fat wasn't very bright. But with fast spin echo imaging, and that's because with long TRs, the fat signal drops off because there's a short T1. And there are also some interaction between the spins that are important. Now with fast spin echo imaging, each of these 180-degree pulses keeps things stirred up, so you tend not to lose signal intensity, and it tends to be brighter. Okay.
The patient's there.
Okay. Okay. So that's the way fast spin echo imaging works. So we do multiple rapidly, closely spaced echoes, each with a different phase encoding, and then we can fill up different lines of K-space. To do this also required modern electronics, because to do this you have to do things very rapidly. So you have to have very rapid switching, and you have to have very high gradients over a short period of time to do the imaging properly. And that kind of electronic technology wasn't available in the early 1990s. It's only now that we have that kind of technology to allow us to do this. So what's happening now, instead of having to fill up one line of K-space every time we do a TR, we can fill up multiple lines of K-space. So if we do a 256 by 256 matrix and we have an echo train length of 16, then instead of having a 256 TRs to fill up K-space, we could have 256 divided by 16. So it would image 16 times faster. So that's how fast spin echo imaging works. And there are a number of ways. This just shows how you can change the phase encoded gradients over time so that each echo is a different phase encoding. You acquire these, store them separately, and then you recombine them to get the K-space values that you need. This would be an echo train length of 8. And here the center of K-space is in the center here. So here it started with high gradients alternating between positive and negative. The center of K-space is out here, and then higher gradients again at the end here. So there are many different schemes to do this to get the kind of contrast that you want.
Dr. Cruz, what limits the how many echo trains you could have in a TR?
Okay, what limits it is how rapidly you can switch the gradients and switch on and off the RF so that you can get the echoes closer and closer together, and how much contrast you lose by spreading the echoes out to different TE times.
Okay.
So if you actually started acquiring data at 15 milliseconds and ended acquiring data at 150 milliseconds, then a lot of some of your data is going to be heavily T2 weighted. Some of the data is going to be heavily proton density weighted, and you may lose a lot of contrast. So what you want to be able to do is center the echo acquisitions around the area of the TE you want for contrast. And in order to do that, if you have too long an echo train length, you're going to spread out the TEs too much, unless you have very fast imaging. Just 1 second. Hi, I'm in a lecture. Can I call you back? Hello? What? Go ahead. Uh-huh. No. The, okay. When I get home, let's go over it, and I'll look it up to see if anybody's using it. And if so, we'll have to cancel it. Okay? Thanks. Bye. Okay. My wife lost her credit card.
Oh my god.
Okay. So, any questions about how fast spin echo works or why we would want to use it? Okay. So, in the old days when we used to do double echo imaging, it allowed us to basically get two images for the price of one. Now, obviously, with fast spin echo imaging, we can be much more efficient from that. And most of the imaging now, we get much better results if instead of doing double echo imaging, we spend that time to do fast spin echo imaging and dedicate each sequence for a given kind of contrast, depending upon what contrast we want. Now,
Sorry, I know I got pulled out. But the key point is on fast spin echo imaging, fat is bright, but it's dark on the traditional old spin echoes. And is that
that's one of the things that comes out.
yeah? What is that? And what was the reason for that again? Was it
The reason is that there when you do these fast echoes, let me think. What's the better way?
which is more reflective of reality? I guess if you could even look at it that way.
Yeah. In the well, I mean, they're both reality.
Yeah.
In there are a couple of reasons why it's that way. One is a thing called J coupling, which I really don't want to go into here, but it has to do with you get crosstalk. You get with these rapid imaging and rapid switching, you get the spins actually talking to one another, which means that the data that you get isn't independent with each one. The other thing that occurs is if you use a long TR, like a TR of 2000, and a long TE, if you have a substance that has a very short T1 time, like fat, then the fat signal, the T1 time is such that, let me think, that's a better way to do it.
Yeah, that's fine. We should just know that's the fact.
Yeah, Yeah, I think it's mostly the fact that with these 180-degree pulses, you you continue to rephase the spins from fat, causing them to continue giving signal back, which doesn't occur when you just have the traditional uh, acquisitions. Um, so now a lot of these ideas came out of a very old pulse sequence, which was one of the early pulse sequences that Mansfield developed back in the 1980s called Echo-Planar pulses. Here you give a 90-degree pulse, a 180-degree pulse, and then there are many different ways to do this, but this is just a very fast spin echo type or gradient echo type imaging. What you do here is you just give a little bit of blip on the phase encoding, increasing the phase encoding. You do a gradient reversal, you get an echo, then you do another blip on the phase encoded, another reversal, get another echo, and you can get very rapid echoes here. Because you don't have a 180-degree pulse on these, it's all gradient echo pulses. You don't have all the RF that you have to put in for regular fast spin echo imaging. And you can acquire up to 128 or 256 images and get an image on a single TR. These kind of pulse sequences, you have kind of a poor contrast because it's spread out in TE, but it's mostly a T2 weighted contrast. The TR is infinite, so you have no T1 weighting in these. But this is one way to do it, and you can get very rapid imaging and kind of real time imaging at one time because the contrast isn't very good on these. It's not commonly used in clinical medicine, but there are a number of ways to do these. And now what's happened is that there's been a melding together of echo-planar and fast spin echo imaging, so that we now typically use, one area where this is used is in diffusion imaging, where you can get rapid data acquisition. But most of the time now we use more of really what should be considered a fast spin echo type technique. But there are many ways to do these, and we don't need to go through all of them. So again, how does this affect scan time? Well, scan time, as we talked about before, is the number of excitations you're going to average together, the TR, and the number of phase encodings, acquisitions. And then now if you do fast spin echo imaging, you divide this by the echo train length. So by using an echo train length of 8 or 16, as we talked about, you can markedly decrease the scan time. Now, we talked a little bit before about steady state imaging. Here you just give bleeps of RF pulse every about 50 milliseconds or so. And again, there are many different ways to do this. But one way is that this pulse could be the initial pulse of the sequence. This pulse could be a rephasing pulse, and then this would be the echo. But if you keep doing that, that means the first one, the first few you usually ignore because they tend not to be in the steady state. But if you keep giving a pulse, say every 50 milliseconds, you'll end up with a steady state position where this pulse will flip nuclei a little bit. These typically are low. They're not 90-degree pulses. They're 15 to 30 degree pulses or less. This will cause some of the nuclei to flip into the XY plane. This will rephase them, getting the echo here. But this one, though, it was the rephasing pulse for some of the spins. It's going to be the initial pulse for others. And you basically then end up with a series of echoes that are typically centered around the pulses. And you can put in gradients here to change the phase encoding. And then you can do images based upon the entire pulse here, though it's a little, usually you'll do one side or the other because you've got the RF pulse here, which will affect your receiving. So you'll either image on the leading part of the echo or the trailing part of the echo, or sum the two together and do an image on both of those. And they're just different ways you put in the phase encoding. And you get different kinds of signal intensity with these depending upon exactly what the TR and TE is. So typically the TR is going to be much shorter than TE because we want to do these rapidly. And so initially what happens is you've got a lot of signal, and then you get into kind of a steady state here as time goes along. Yes, ma'am. Yeah, it's Dr. Villa. Could you ask him if I could call him back in 30 minutes? I'm in the middle of a lecture. Okay. So, I don't want to bore you with going through all these little details. The bottom line is you get the echoes, and there are different parts of the echoes that you can use to acquire images. And the whole steady state free precessions can be called spoiled gradient echo sequences. Let me see if I can go. No, never mind. And some of what typically you get with these images, most of the time what we use them for is since you're acquiring data about every 50 milliseconds, you can get very rapid imaging. It's typically or often used in a 3D technique. Since you're acquiring data rapidly, you have time to do phase encodings in two different directions so that you can do 3D imaging. And most of these tend to be very sensitive for fluid. So we use these sometimes in joints, especially after contrast administration for gadolinium to get high 3D resolutions of the joints. We can get them in the cervical spine to try to get high resolution of the neuroforamina with fluid in the CSF being bright. So there are a number of ways to do these images, and they come with all kinds of different names from the different manufacturers. The bottom line is that they're steady state sequences, and you typically, as I say, they have many, many different names, so you tend to pick the one that gives you the kind of contrast you want in that particular area. And in practice, we can talk about some of them. Now, let's go on and talk about some other sequences here that you'll occasionally see. One is called magnetization transfer. Aram, do you know what the term magnetization transfer means?
No, I just remember that neuro guys used to use it in the post-GAD sequences to increase enhancement.
Yeah, post-GAD, but it often has been used in the past in non-contrast angiography because it suppresses the background signal, making better contrast. Here, it's the situation that when you look at water in the tissues, you have a big peak from free water. But then what happens is that a lot of the water is not freely moving in space like in the bladder. A lot of the water is bound to macromolecules like within muscle and so forth, where they're fixed on or adsorbed onto large macromolecules. As such, they tend to resonate at a different frequency than the main water peak, uh, uh, primarily due to shielding electrons. So it was found a long time ago in biochemistry that if you put in a saturation pulse, so that you take the Z component of the bulk magnetization vector in this area of the water to zero, then if you then look for the strength of the magnetic field, so if you gave if you saturated the spins here and then did a spin echo, you would end up with a lower signal intensity than if you didn't saturate the spins here. If you're imaging in this area at this frequency, which is where these water is. But a question that people wanted to know years ago was, does the water in the macromolecules freely exchange with the water in the free water space? And the question is, nobody could really answer that until MR came along. And then what we found out with MR is if you put a sat pulse over here, which doesn't affect the free waters, if you saturate the bound water, well, let me put it this way. If we do an MR of the free water, when you have no sat pulses, you'll get a very strong signal. If you put a sat pulse in the bound water and then redo your experiment again, If you get a drop in signal intensity within the free water, that means that the saturated nuclei from the water from the bound portion has moved into the free water portion and is saturated and won't give a signal. If you do a sat pulse in the bound water over here and you get no change in the signal intensity you get from doing an MR experiment in the free water, then there will be no interchange of water between the two. And it turns out in a lot of biologic tissues, there is a free exchange of free water between the two. And in the early days, we tried to see whether we could use this for looking at articular cartilage, thinking that if you had damaged abnormal articular cartilage, you might have more mobility between the bound and the free water. And we really didn't find that that worked very well. But what happens here then is if you have something like a MR angiogram of the brain, there's a lot of the water that you have in the brain is associated with the large macromolecules of the brain. So if you do a magnetization transfer pulse, that's what you'll find is in the area of the brain where you have a lot of water associated with macromolecules, you can decrease the intensity of the signal from the water in the brain. But since you do not have a lot of macromolecules in the vascular space, it doesn't affect the water in the vascular space. So you can suppress the signal intensity from the background brain substance and bring out the signal intensity from vessels and therefore increase the contrast in vessels. So a lot of the angio sequences use magnetization transfer to improve the contrast of vessels. This is just from trying it on cartilage. Okay, so those are some of the little bit more esoteric areas. Let's go into something that we do all the time again, and that's fat suppression techniques. So especially in the musculoskeletal system, we do these every day, and there are a number of different ways that people can suppress the fat. One is chemical selective fat suppression, spectrospatial water excitation, stir imaging, chemical shift or Dixon technique, and steady-state free precession type methods. Most of these hinge upon the fact that water and fat resonate at two different frequencies. In fact, at 3T, as we know, there is a 420 hertz difference between the fat peak, the main fat peak, and the main water peak, which we see here. So one of the things that can happen is if you put an RF energy in the area of the fat before we do the signal and make sure that the RF energy is just at the frequency of fat and with no energy at the point of water, then you can suppress the fat signal and have it go away so that you only get a water image. And this is what we typically use, call it fat sat imaging. And you're familiar with those images. But one of the problems with using fat suppression is that it's very sensitive to magnetic field inhomogeneity. And we see this all the time. We call it failure of fat suppression. If it turns out that that the magnetic field where we're located is higher than we expect it to be, well, then what can happen is that neither the fat nor the water will get the RF energy, and so neither will be suppressed, and both will be bright, so it'll just look like a typical T2 weighted image. If the field strength is, field intensity is too low, then the RF energy can actually be at the water peak, and you can suppress water and not suppress fat. And then you can also do different levels of RF energy so that you either completely or incompletely suppress the fat if you want to keep some of the fat signal there. So the biggest problem there are two problems that we have with fat sat imaging. One is that you really have to have uniform magnetic field. So in the periphery of tissues like in the shoulder or in the foot and ankle or elbow will often get failure of fat suppression. The other is that this is a lot of RF energy, and if you're dealing at high field where you already have a problem with high SAR values, this adds a lot of SAR to the images and can cause tissue heating, which may have to limit the pulse sequences you do, especially if you're not using a send-receive surface coil. And this just shows an example. If this is the water peak and that's the fat peak, there's where we put the sat pulse. It should just suppress the fat and not the water. But if the field is abnormal, we can suppress part of both. Or if we have very low field in that particular area due to inhomogeneity of the field, we can just suppress the water. And those are the main things. And this is just an example. This is a patient who came in where this MR was read as osteomyelitis. However, the patient had no symptoms at all of osteomyelitis. The patient actually had pain actually more around the midfoot area. So the referring physician questioned the reading, and what we can see here is on the T1 weighted images, everything looks pretty normal here, but we see kind of a diffuse increased signal intensity on the T2 fat suppressed images. But if we do stirs, everything looks very normal. And so what this is a failure of fat suppression here, and that's what it looks like. And that's because we have inhomogeneous field, and the magnetic field in this location was go back here, was too high, so that actually both the water and the fat were shifted out of the saturation pulse, and neither were suppressed. And so both are bright. Here's an example of a patient who came in with lateral epicondylitis. Here's the PD fat sequence, and you can see right away that you have problems. You can see that there's no suppression of the subcutaneous fat or the fat within the marrow space of the proximal radius. And we see a lot of signal loss over here in the area that we're interested in. So this patient was brought back and did a stir sequence, and you can see that there's a partial tear of the common extensor tendon that you can't see on the fat sat image because both the fat and the water have been suppressed here, because this is a local area of field that's too low, which shifted everything into the saturation pulse. And this is what the T1 weighted image looks like in that location. So whenever you see this kind of inhomogeneity on the fat sat image, you've got to be very concerned about it. You can see it due to the inhomogeneity of the field, or you can see it also if you have metal or other foreign body artifacts within the image.
I'm still confused. Like, are we changing the field of view? The field of view, like the size of the image, looks the same. So
It is the same.
what we're changing from PD to the stir. I mean, besides like the characteristics that it's a stir versus PD, but like why for we have a smaller field of view, generally we do a PD, and then if it's a larger field, I thought we did stirs.
No, that's not true. No, you use both of them with the same fields of view. It has nothing to do with field of view. We use PD images. If you use PD fat sat, you typically get images of higher signal to noise than with stir. So we tend to like to use PD fat sats at high field whenever we can. However, there are two problems with, I mean, the biggest problem with PD fat sat is the inhomogeneous field and failure of fat suppression or oversuppression like we're seeing in this particular case. And there the stir images are very helpful. The other problem with fat sat image is that they're very sensitive to metal artifact. So we tend to use stirs whenever there's metal in the image. And if we do a knee study and there's an ACL and they use metal interference screws, then we always ask them to add a stir sequence because it's much less sensitive to metal artifact. The other area is most of our protocols in dealing with the periphery outside of the knee, like the foot and ankle, is we will usually do a stir sequence in the sagittal plane where you tend to get most of the failure of fat suppression, and we typically use a PD in the coronal plane where there's less problem with failure of fat suppression. But we will use both then simply because we have a high rate of getting failure of fat sat and imaging of the foot and ankle. Now we'll go to another sequence here in a minute which gets rid of all of this problem, which is an ideal sequence, but we haven't gotten there yet.
So how come for like imaging we don't do PDs, we do stirs?
Because you get more failure fat suppression in body imaging, especially on 3T scanners. And therefore, we use stir to decrease the amount of failure fat suppression we get. If you noticed on the low field of those, we do a smaller field of view image, and there the large field of view, we tend to do stir, but that's just because with the large field of view image, you can get a lot of variation of the magnetic field over a large field of view, and you tend to get a lot of failure fat suppression. When we go to the smaller field of view, we'll often do PD fat set because you've got a more uniform field over a smaller area, and you tend to get a little bit better signal to noise. So I guess
Dr.
there are
Cruz, why,
some sequences where we do the PD fat set for smaller field of view. That's the reason. Yeah.
Yeah.
Dr. Cruz, why do you get the failure of fat saturation in the sagittal more than the coronal? Is that because of the phase and frequency, or?
No, you shouldn't. That would just be characteristic of well, there are a number of things that can occur. One is that could be something that has to do with your magnet, and this tends to be, each magnet is a little bit different in terms of its shimming. It could be due to the way your shim is on your particular magnet. It can also have, there's also an effect that has to do with the transmit coil. If there's any inhomogeneity, the B naught in the transmit coil, that can also affect the amount of energy which your suppression sequence pulse puts into the tissues in a different location. So there are a number of different things that can cause inhomogeneities in, in the object. But the coronal or sagittal plane, generally there shouldn't be any difference.
But didn't you just say that you had more failure in the sagittal plane than the coronal, or did I misunderstand?
I see. In the foot, the width of the ankle in the sagittal plane is much narrower than the length of the foot. I mean, the width in the coronal plane is much narrower than the length in the sagittal plane. So you only have to have a uniform field over a small distance in the coronal plane to cover the ankle, whereas you have to have a uniform field over a much larger area in the sagittal plane because you're going from the calcaneus all the way down to the metatarsal basis. And that's why you tend to get more of a problem in the sagittal plane with failure fat set than in the coronal plane.
Gotcha. Okay.
Okay. Now, the next technique that can suppress water is called spectral spatial water excitation, where we can just excite water and we don't excite fat. The way this works is if you start out with your bulk magnetization vector in the z direction, and water and fat are both pointing in the same direction here. And then if we do a small pulse, let's say something like a 33-degree pulse, you'll rotate both water and fat 30 degrees into the XY plane, and then this whole thing, this bulk magnetization vector, starts spinning around. But remember, fat and water spin at different frequencies. So then if you wait a small amount of time, you'll find that fat and water will be 180 degrees out of phase in the XY plane. If at that particular time you put in another alpha pulse, in this particular case, fat is swung all the way around to the other side, then if you do an alpha pulse again, you'll rotate the fat back up into the z-axis, and you'll rotate the water farther from the z-axis. And then here's a situation where the rotating bulk magnetization vector now is all water, and fat is no longer rotating. It's just in the z direction. So here, all the signal you would get would just be from water. Again, this uses the difference in the frequency, the Lamar frequency between the two structures, and you obviously have to time it just right in order to do that. Another technique.
Is that not stir? That's not a stir sequence?
No, a stir sequence, you start with a 180-degree pulse. To invert it, and then you do a standard spin echo image with a 90 and 180-degree pulse. This you just give a two two small pulses at the same angle timed just right so that you end up only exciting water.
Would we see? Is there any sequences that we look at on a daily basis that utilize this, or is it a little
No,
fancier?
not really. I don't think this is used much right now. There's a type of this that we'll talk about in a minute, ideal, which is kind of like this, but much more sophisticated. Another thing is called the Dixon technique, and a Dixon technique is very similar to what we just talked about. Here you give a 22.5 degree pulse, you rotate both water and fat in the plane, then you wait until they get 180 degrees out of phase, you put in a 45 degree pulse. That rotates the water down almost to the XY plane, gives a little bit of rotation to the, it flips the fat back over into the same direction but at a less flip angle. Then you wait again enough time for their 180 degrees out of phase. You give another 22.5 degree pulse that rotates fat up into the Z-axis again where it's not rotating anymore, and the water is now in the XY plane where it gives a strong signal rotating around in the XY plane. So that's another Dixon water technique. Now, the limitation of this and this particular technique in its more modern phase is called an ideal sequence. The limitation of this is you really can't do it at low fields. It's somewhat limited, but I mean, you can do it at low fields, but you have limitations. It's better to do this at low fields than it is to do the fat suppression because, again, the separation between fat and water is higher at higher field strengths. And if we go back to this, you can see that the more you separate the fat and water, the less likely you're able to get these artifacts, which we see here. And at low field, the fat and water are very close to one another. At high fields, they're very separated. So the fat suppression is much easier to do at high field. In fact, none of the low field scanners that I know of have ever been able to do that because there's too much overlap between the water and the fat peaks. This technique is also very sensitive to magnetic field inhomogeneities. Now, inversion recovery, stir sequence is another sequence that can suppress fat. We've already talked about this a couple of times. If you do an inversion pulse and then wait for the spins to recover along the z-axis, if you wait a short amount of time, the fat will have recovered up to zero. If you then do your 90 and 180 degree pulses, there's no z component of the bulk magnetization vector for fat at that point, and so it will give no signal. There's a lot of Z component of the bulk magnetization vector for the other components like water here, so they'll be rotated in the XY plane, will spin around and give a signal. So the original reason that stir was invented by Graham Bitter was to suppress the fat. In that particular case, it was primarily the fat signal from the skin around the chest, which gave artifacts from breathing. So that's the stir technique, and that's a very robust technique. We use this a lot in imaging, and it's insensitive to magnetic field inhomogeneities, which is helpful. It does require a longer TR to do it. All tissues are affected based upon T1. So the problem with this is you've got to be very careful in using this when you have contrast, because as we talked about before, the way contrast works is it shortens the T1. But stir limits signal based upon T1. So if you put in contrast and you shorten the T1 of a tissue down to where it's the same T1 as fat, then instead of being bright like you would expect contrast enhancement to be on a stir sequence, it will be suppressed and it will be black. And that can cause artifacts that can be misinterpreted if you're not careful. So the bottom line, unless you're very careful, you should never use stir imaging when you give contrast. Okay, here's just an example. Here's somebody who had an arthrogram of the knee. This is a stir in the coronal plane, and it looks here like there's a loose body within the joint space. But if you looked at this on the T1 weighted image, there doesn't look like there's anything there. And what happens is that the T1 of the contrast in this location is the same as the T1 of fat, So just in that area, it's being suppressed as it would with fat. And it's an artifact, and it's not a loose body. Okay. Now, another technique is a chemical shift Dixon technique. When you first have fat and water, and if you give a pulse, as we said, the fat and water will rotate into the XY plane. They'll precess around together, but at a point they'll be out of phase. And typically, well, out of phase. And then if you take an image, both an in phase image and an out of phase image at two different TEs, then there can be a difference in the signal based upon whether or not you have both fat and water in that voxel. And again, that's, as we talked about before, this is a way people look to see whether or not there's a tumor in the adrenals using gradient echo images. You pick a TE when they're in phase, a TE when the spins are out of phase. If there's a difference between those two, then you know there's fat in the voxel. Tumors tend not to have fat in them. So if there's no change in the signal intensity, then you know you do not have fat in the voxel, and you have to be more concerned that you might be dealing with tumor. That sometimes can be helpful in the bones as well. So this is a technique where you use at least two different acquisitions. Usually use three, another one to correct for phase problems. Uh, and if by acquiring three, you can decrease the sensitivity of this technique for magnetic field inhomogeneities. And this is used a lot at low fields. This is a very good technique for low fields. Here's a T2 weighted image. Here's a fat suppressed image using the Dixon technique, where you use in phase and out of phase imaging to get the fat suppressed technique. And this is used a fair amount at around 0.3 Tesla. You can either use stir techniques or the Dixon technique at low fields. Because multiple images are acquired, it often takes longer, and the quality often depends on field inhomogeneity. The more advanced way to do this, where you can maximize the amount of information you get per unit time, is a technique called an ideal technique. It's first kind of developed at Stanford, and then at the University of Wisconsin. And here's a technique where you can get a water image, a fat image, and here's the combined image between the two. You can also get an in-phase image and an out-of-phase image, all with a single acquisition. These are very insensitive to field inhomogeneities, and they're also very insensitive to metal artifacts. We only have this on a few of our scanners right now. Dr. Fatemi and I like to use this technique, especially in the foot and ankle. I like it in the other joints as well, though some of the other doctors tend not to like the contrast quite as much. One of the things, the fat suppressed image looks very much like a PD fat sat image as far as contrast. The other thing here also is that there's no chemical shift artifact with this technique. It's there, but it's known what it is. You get a fat image and a water image, and you can correct the images because you know what the chemical shift is. So the images you get are actually corrected for chemical shift. So you can see here that the thickness of the articular cartilage is basically the same on both sides here. So we don't have to worry about chemical shift artifact, which you have with all the other techniques. The one thing is that the in-phase images look very much like a PD image without fat suppression, except fluid is bright, and it tends to be darker on a PD type image. You can do it with gradient echo techniques or fast spin echo techniques. And well, let's see. Here's just a fat suppressed gradient echo technique using gradient spoiling. Here's a fat technique using ideal, or this is fat suppressed using a steady state free precession, and here's an ideal technique. So you can see here the three different contrasts. So this would be fat suppressed gradient echo, kind of a fat suppressed steady state technique, and here would be the ideal technique. And the thing is, with ideal, you tend to get bright fluid where you don't in a spoiled gradient echo. This is typically what the images look like. Here would be a water image. Here's a fat image. Here's an in phase, and there's an out of phase image. The out of phase tend to be very sensitive for bone injuries, but most of the time, when I look at these, I read the water image and the in phase images, which look very much like a PD fat set and a proton density type image.
What's the other two then? What's on the upper right?
This is a fat image, where the signal intensity is just dependent upon the amount of fat in the voxel, and this is an out of phase image. Okay, and here it is in the spine.
Why do you particularly like it for the ankle?
The reason I like it for the ankle is you don't get any failure fat suppression, which is often a problem in the ankle. A lot of the ankles we've read recently, there's a concern about whether you have failure fat suppression or whether you have edema within the malleoli. And you don't have that question when you do ideal imaging. You always get uniform fat suppression. Okay, and then this just shows how this would be a image of two cylinders, one with fat, one with water, showing the chemical shift artifact that we talked about before. But with ideal image, you can correct for that and you get no chemical shift artifact. So it's great for cartilage. So why don't we stop here and we'll start again and go through the rest of the pulse sequences. Now, I'm not going to be around next week, so our next lecture will be a week from Monday. Okay? Any questions? Thanks.